short introduction, and then hand it over to our chair, Dr. Sanchez. So, 2-second introduction. It's my pleasure to introduce Peter Harnish, who's been with us for the last year and a half or so at the University of Vermont. And the two most important parts of his biography are that he grew up in Athens, Ohio, which is home to Ohio University, and he graduated from Miami University, which is in Miami, Ohio, with a BS in physics and BA in chemistry. So we won't hold that against you, the chemistry part. And he's been here for the last year and a half, and I think it's fair to say from last summer, about 8-9 months ago, he started working on graphene. He joined our ongoing research on van der Waals interaction, which we'll be talking about, as well as he's been working on another project, which is the second part of the talk. So that's it. Thank you very much. And I think you have the
well, so as a matter of process, let's see. We'll do this in 2 stages. So we'll have the open discussion. Everybody will be able to ask questions at the end of your talk. And if the committee can ask questions, if it's for clarification. So who is the committee? Adrian?
Yeah.
Yep. And me. So you can ask questions for clarification. The talk, and then we'll ask the audience to leave. We'll have a closed session with the committee. So this, I understand, is just your proposal.
Yes.
Okay, so it will be mostly advices. Okay, and I hope your presentation is not too long as a proposal.
I'll try not.
Okay, so we'll stop you after 1 hour and a half of presentation.
Shouldn't be that
now.
I raise my hand after like 30 minutes. If you exceed 30 minutes, that's way too long. Okay, we'll keep it short and concise.
Okay, I'll do what I can. So, Chris, if you want. Hey. Yeah, so I'm Peter Harnish. The research I've been working on is electronic correlation effects in strained dual-layer graphene systems. I've been doing this work with Dr. Larry Kotov and Anand Sharma, and last summer we borrowed Alexander Sylvester from McGill University as an RAU student. So what to expect today is kind of just what we do as a research group, and then in increasing complexity, our work of van der Waals interactions, and then into kind of what I'm specializing in, the excitonic pairings, in a slightly different system, and then where we hope to go after this. So starting off with graphene, I know a lot of us know a lot about graphene, but just in case. Graphene is a 2D carbon crystal. So it is a 2-dimensional crystal. It's completely flat. It has an AB sublattice, which means if we look here in the picture, all the reds are identical, all the blues are identical, but you can't swap from red to blue. There are 2 kind of bonds that keep together. They're the sigma bonds, which form the trigonoplanar dimension, which provide the tremendous strength of graphene. And then there are the pi bonds, which exist out of the plane, which is what we get the amazing electronic properties from. For people with a little bit more of a chemistry background, the 2 things to note here are that you can think of graphene as an infinite sheet of benzene rings. So the same way that the electrons dissociate on the benzene rings, this happens across the entire crystal. Talking about the directions in graphene, the 2 phrases you'll hear a lot are the zigzag direction, which is this way because it's all zigzag, and then the armchair direction because it's thought that that looks like a chair. So the armchair direction, which we often refer to as Y. Graphene, as a word, first showed up in the 1840s. It was used to describe the single layers of graphite oxide that people were studying then. Then the next time it really came up was in the 1930s, when using thermodynamics it was proved that it is impossible to exist in the world. There's no way that you could have graphene existing. And then in the 40s it was studied as a thought experiment because we were working on graphite research. And the simpler model to think of is just 1 layer of graphite, which is then graphene. And then of course the big news, in 2004, we were able to prove conclusively that we've had graphene for 400 years. Every time you break a graphite, you will produce graphene. It's just so small that it hasn't been noticed until 2004, which is part of why that got a Nobel Prize. The big ways that we get graphene are, the first attempts were through the reduction of graphite oxide, which is chemically messy and not, doesn't produce that nice of systems. Exfoliation, which is the Nobel Prize of literally taking Scotch tape, putting it on pencil lead and producing graphene. And then really, one of the more interesting ones, chemical deposition, that if you take hydrocarbons under very low pressure, they will deposit a single layer of graphene on a metal foil. Copper seems to be what's going the best. At the APS March meeting, in a graphene seminar that I attended, they were quoting that they can now make square centimeters of perfect graphene, which there are these huge advances in making graphene. To give you an idea, in 2008, the price of graphene was $100 million per square centimeter. As of last week, there are catalogs where you can get it for $400. That's how quickly we're getting good at graphene now that we know we can. And graphene has a bunch of possible applications because it has all these interesting things of photodetectors and integrated circuits and all this. And most of those interesting things come from this energy band structure that it has. So looking at the energy band, just the standard valence and conduction bands, we have these very interesting points here on the corners of the Brillouin zone. And if we zoom in on these, we get this very interesting linear dependence with momentum. This is the classic Dirac cone that shows up. And I don't want to say by coincidence, but the math to describe the movement of the electrons in these low momentum regimes is the same as the Dirac equation. So we can talk about electrons moving in graphene as if they are spin 1/2 relativistic particles, with the caveat that the Fermi velocity is 300 times slower than the speed of light. So there's a lot of interest in that's relativistic behavior within the realm of what we could actually see and manipulate because it's so much slower. Now, what we specifically like to do with graphene is what happens when we put it under strain. So when we talk about strain, we're going to be talking about uniaxial strain, which means we're straining only in one direction, and that direction will always be either along a zigzag or an armchair. Now what's interesting about this is that the strain causes a preferred direction of motion. So as we see here, straining along the armchair, it's easy to imagine that electrons would prefer to move along this zigzag as opposed to the armchair where there are these large gaps. So this preferred direction of motion then creates preferred velocities, which then creates preferred momentums. So that manifests as the Dirac cones become elliptical in nature, which then presents some interesting dynamics to talk about. We work mostly by talking about these as velocities, and there are two basic ways that I'm going to talk about strain. The first is through this epsilon, the strain factor here. But that only really is applicable in small strain. So what we tend to prefer is instead this v perpendicular, which is the relative velocities of the y direction and the x direction. So as we strain in the armchair direction, the velocity in the y direction is going to decrease compared to the x in the x direction. So we get this v perpendicular. One of the things that we really like about talking about it as this ratio is then we can talk about strain just as this number between 1, the completely isotropic case, when they're the same, to 0, when they're strained to the point that one direction is infinitely slower than the other direction. And it really cleans things up a bit as opposed to talking about in these epsilon factors. Now I say infinite, which always worries people when we talk about experiments. So in extreme strain, we do get a very interesting behavior. If we strain very severely in the armchair direction, the travel in the armchair direction becomes so minimal that in essence we end up getting these one-dimensional wires, right, that are just coupled physically. If we strain in the zigzag direction, we would then start to get these merged Dirac cone pairs. And this is very interesting and very weird, to the point that most of the time we're going to pretend it doesn't happen. I know pretending it doesn't happen doesn't sound very good. But to give you an idea of right now, experimental strain maxes out at about 5% strain. And these features are going to show up at 70% strain, 80% strain. So right now, we feel comfortable assuming that our graphene is going to be homogeneous in nature, and we're not going to, and straining significantly in the x direction is going to look the same as straining significantly in the y direction. So we're not going to worry that carefully about these specifics of extreme strain. Now, in building our structure, graphene, as I mentioned, has been studied theoretically since the 40s. So work on just a layer of graphene is pretty well done for the most part in these kind of electronic properties that we're talking about. So naturally, the next step is to build more complex systems out of these simpler systems we know. So two of the big ones that you hear a lot about, there are these superlattice structures, which we've had some colloquiums about, where with moire patterns we start to get larger lattice structures and these kinds of things. And then more towards what we're doing is these multi-layer systems, where you can imagine taking two layers of graphene, and if you get them close enough, they now form a bilayer, where you just have these two layers like the beginnings of graphite, which then shows different behavior than just graphene or just graphite. So there's a lot of study in these building of complex systems. But the system that we're going to focus most on is this. So we have two parallel layers that are suspended in space, so they're not on a substrate. And they're infinite sheets. By infinite, I just mean large enough that there are no edge effects that we worry about. So infinite in the same way that we worry about infinite capacitors, just there is no edge to what we're studying. And when we have them suspended, we always have the layers aligned but not stacked. That means that we always have an armature directly above an armature, but we don't care if the red is above a red or if the red is above a blue. And that's because our separation distance is on the order of a nanometer or more. To give you an idea of scale, the distance between these carbon atoms is about 1.4 angstroms. And if you get these two layers to within about 3.5 angstroms, they'll start to bond and form graphite-like structures. But we're staying up at 1 nanometer. So there's no tunneling between the layers, there's no possibility of electrons moving between. We're just sticking in the long-range Coulomb interactions. And then these layers are suspended in a material of our choice, where the effective interaction, this alpha, can be anywhere from 2.2, which is a pure vacuum, down to 0, which is so much stuff in there that the two layers are completely screened from each other and there's no communication. So starting with the simplest model for this, which is going to be those two layers, completely neutral, nothing else going on with them. What we're going to end up seeing are these van der Waals interactions, are the first place we can look. So just a reminder about van der Waals interactions, that in general there are several related forces that get clumped together to talk about van der Waals. The main thing is that there are dipole-dipole forces. So these can be permanent or induced dipoles, but they're the forces between neutral systems. So there aren't charges on the individual layers. And what we're concerning ourselves with is kind of this region of the van der Waals forces, where they're going to show up as an inverse quadratic of the distance between our layers. So we're expecting forces that will go as negative over d to the fourth, with some coefficient that we're going to worry about. So describing our system, we get a force that looks like this, which will be gibberish to most people. So in essence, what this boils down to is there's a polarization from the layer 1, this potential and polarization from layer 2, and then over some screening effects that happens between our two layers. To clean up this math a little bit, we get this condensed form, which we're particularly proud of because of this G term here, which has these two sections which are purely the physical conditions of each layer. That we can boil it down to just talking about the potential and polarization in layer 1 and the potential and polarization in layer 2. And then as we change these systems, that's where our interest is going to be. So, how are we going to change these systems? Strain, that's what we do. So how will strain alter these systems? As I said before, strain causes preferred directions of motion. So now we have to start worrying about this anisotropy between the layers, that the velocity in the x direction and y direction aren't going to be the same anymore. So with that in mind, we have to generalize these potentials and polarizations. So here we have the Vx and Vy come out independently, and then we also introduce this phi just because we have to worry about a generalized angle, just the normal polar kinds of things. And in this form, we can then dimensionalize this, where we get, once again, we pull out this g, which is purely about our two layers, but also we get this negative d to the fourth term all the way out of our integrals. So now we're purely talking about how that coefficient is going to be changing. We don't need to worry about this general d dependence between our layers. So in the isotropic case, we get nice and clean like this, but then we want to study anisotropic cases. So the first case is going to be the single strained layer, where we have one layer strained in the armchair direction. And this shows nicely how G works. That one layer looks exactly the same as the isotropic, because it is isotropic. And the other, we introduce this strained case. The next case we're worrying about is both of them strained. So now they're both strained in the same direction, so these terms end up the same. I won't go over it here, but we have done the math for if they're strained independently of each other to varying levels, and that just shows up as you'll have a V perpendicular layer 1 and a V perpendicular layer 2, which you can then slide independently, but the math ends up being effectively the same. And then we also have perpendicular strain, where one is now strained in the armchair direction and one is strained in the zigzag direction. So, what becomes of all this, we get here. So these are the results. This is the coefficient of each anisotropic case, scaled as a function of the isotropic case. So we're just getting a percent increase, if you will, of the single strain case, the perpendicular strain case, and the parallel strain case, which we get this remarkable, almost an order of magnitude increase from straining these layers. Now, this is, and you can see that also as we decrease that effective term between them by decreasing this alpha, so more and more screening effects, these only get bigger and better. But we have done a bit of a simplification to get here. As I said before, we completely removed this D dependence. But it's not quite that simple, because as we strain, that straining is going to change this alpha. Changing the alpha is going to change your velocities. So it's actually a bit more complicated than that. And we have to worry about how all of these terms are going to change together as a group, which we can do through renormalization. So here we're in the weak coupling approximation, so that's alphas that are smaller than 1. We are going to introduce this additional distance dependence. So in addition to that d to the fourth, we also now get an additional d dependence. And we can see, just kind of looking how this is going to go, since we're in the weak coupling approximation, we now have alphas in all these denominators. So that's going to hinder things a bit. We also now have the strain case in each, in the denominators. So that's also going to lower things a little bit. So we expect a little bit of a decrease here, which is exactly what we see. So these are all at alpha 0.5, and we can see that as we increase the distance between the layers, all of these terms go down, which is what we expected, but interestingly, not something that most people spend time to look at. From what we've found, not many people have worried about these multi-body corrections before. And as you can see from here, they're very important. And it's really something that can't be ignored, but we find a lot of people are. So we're very happy that we found these, because as we move forward in this research, we now understand that these corrections are going to be rather important. So as we've seen here, that strain increases the van der Waals interactions in the most optimal cases, up to an order of magnitude increase. But as we do these renormalization effects, there are going to be consequences that we need to worry about, and it's something we need to pay attention to as we go forward. And these results are van der Waals interactions. We have put together here. This is currently in the review process at Physical Review B. I believe we have submitted our first rebuttal. So hopefully this will be coming through pretty soon. this is the research that we did with Alexander, and kind of the first project that I came in on. And as we went from here, then the next question after this is going to be, of course, how can we get a slightly more interesting system, put another layer of complexity on it? So previously we had these neutral layers, and we could only talk about the neutral interactions between them. So that then begs the question, what if we don't have neutral layers? What if we charge these layers? We put an electronic bias on them. And that opens up the door for excitonic pairings to happen. So now, we're in a very similar system, except in this case, we're now putting a bias across the levels, which create a population. So we now have one graphene layer that has a population of electrons, and another graphene layer that has a population of holes. For the sake of our preliminary exploration into this system, we always assume that the biases are equal but opposite, and we're only going to worry about strain in the parallel dimension at the same time, just as a starting place for this research. So since we now have populations, we have electrons and holes in this system, it could be possible for these electrons and holes to pair by these Coulomb interactions, which could then cause electron-hole, which in theory could then produce things like electron-hole condensations. We could get these BCS type effects, which would be great and very interesting. But so far no one has seen this experimentally. And the reason for that is probably that the pairing is too weak, meaning that the gap is too small. But we now have strain, which we've seen do amazing things. So we wonder if strain could help this case out. So now that we have this bias that changes our math a little bit here, we now have a density of states since we have a population, and that's going to be dependent on that bias. Since we now have a density of states, that's now going to show up in the static polarization. Because it's graphene, we end up with some chiral terms, just due to the nature of the AB sublattice. And then from there we can get towards BCS type math, because we know where we hope this to go. So using a constant gap approximation, and the L equals 0 case, in all of the previous literature we found, all of them cite that the S-wave solution, the L equals 0 case, seems to be where all the predominant effects are, where if this is going to happen, this is the best case. So we feel comfortable limiting ourselves to the L equals 0 case to begin with. We're also sticking in a low momentum regime to try to take advantage of the interesting low momentum characteristics of graphene. And we end up with a very nice gap equation, which all kind of depends on this lambda, which is from our density of states and our effective potential, which written out explicitly here with some dimensionless variables just to try to make the math clean. So then, obviously, the question we want is, how will strain affect these pairings? So now, once again, because of the anisotropic nature, our velocities have to be treated independently. So we now have Vx and Vy. This separation of the velocities is then going to ripple through everything else. So we now have scaled potentials and density of states. We scale our variables to accommodate for this. One thing that is to note is that by the way we've done this, this 1 plus theta, cosine theta, this pairing angle term, due to the chiral nature of this, comes out completely unscathed, which is by our own doing. What we can do is all the anisotropic behavior in the graphene we can force into the momentum instead of worrying about the pairing angle. So you can think of it the same way as if you have elliptical system, you can put parameters on your distances and then treat it like it's a polar system instead, which is what we do here, so that none of the math of the pairing angle gets messed up as we put strain on this system. So then the question is, how will this lambda change as we apply strain? Which is at first less than what we hoped. Well, I don't want to say that. This is kind of what we expected. That as we apply strain, the opportunity for pairing between the layers is going to decrease as things are going to be confined more and more. But once we have this set up, of course, you have to run through all your possibilities because you already have the program. And we've got something we didn't expect, that as we lowered alpha, as we increased the straining on this, we actually start to get this crossover regime, where at this increased screening, we can see we start to get an increase on strain. And if we go to small enough alphas, we start getting considerable additions to this. But before we can get too excited about maybe going into a lab and finding this, the absolute values of these lambdas are still on the order of 0.02. And this gap is going to be the exponential of minus 1 over lambda. So we're still looking at gaps here that are along the order of orders of magnitude under electron volts, which is not really within the realm of what we can find experimentally. But it definitely gives us hope that with the right combinations, we might be able to juice it up to where we can see something. So in this work, we've seen that the excitonic pairing is definitely affected by strain. It's also very sensitive to the interlayer distances and this effective interaction potential, this alpha, to the point where at large alphas, we see a marked decrease. But at small alphas, we start to get an increase here. So where can we go from this? As we showed in the van der Waals case, we know that this renormalization effect could be very serious. And we haven't applied the renormalization to this really just because we haven't gotten there yet. This is where we hope to go. But we know from our previous work that this multi-body correction is going to be very important. One way or another, we need to go through this. And then also, as I said at the beginning of this, so far we've only done the parallel strain case. We started there because out of hope that previously the parallel strain case was where we got our best results, thinking that might happen here. But based on this, we think maybe it might be inverse to the van der Waals case, of maybe at other strains we could get better results. And then of course, right now we have equal bias applied to both layers. And we need to know what happens if we change those biases, if the electron hole populations are different. And then, hopefully, with this kind of information under our belt, we hope to get all this excitonic pairing into a publication this summer. And I hope to write it up as a thesis. Are there any questions about this?
How do you get a uniform state of strain in graphene?
How are we straining?
Yeah, how do you get a uniform state of strain?
Yeah.
How would you tell an experimentalist to get a uniform state of strain?
That is a conversation I got into at APS. That is more complex than I thought it was going to be at the beginning. From talking with experimentalists, it seems the most promising way to get a uniform strain is through a substrate. That if you take that there's a lot of interesting work being done with putting graphene on a insulating polymer base, and then you can stretch the substrate. And if you've uniformly attached the graphene to the substrate, then you should be able to mirror that strain in the graphene. Then the other things that we're able to...
So if I provide a tensile force to a sheet of graphene, will that give me a state of uniform strain?
I think so. That it should strain pretty uniformly across.
So there's no Poisson effect with graphene? Usually if you pull on a material,
yeah,
then it shrinks in the transverse
direction. So
does graphene have a Poisson ratio?
No, this is absolutely true. I kind of grazed over it because we tend to think of it as a homogeneous system. But here, that as we put strain, we are decreasing one velocity and increasing another. Because as we strain in the y direction, the x direction will pull in a little bit.
Yeah,
But-
right, so the ratio of the two is called the Poisson ratio.
Yeah.
So what's the Poisson ratio in graphene?
Let's see, that's sigma, which, the number is escaping me right now. I know, I have it in my calculations.
0.165.
0.165, thank you. So it is there in the math. We do account for it when we're doing these epsilons. And then when we switch over to relative velocities, we kind of put it a little bit under the carpet. But it is definitely considered and is present in the math.
I just had another question about the mechanical properties.
Absolutely.
Is it elastically isotropic, graphene? I mean, it's a hexagonal crystal, right?
Yeah.
On the atomic scale. So it might be the case. I don't know what the elastic constants look like. That it's isotropic or nearly so. Is that
Honestly,
the case with graphene?
I do not know either. I have not.
So it
Dr.
depends on
Sansos
the
probably
applied.
knows.
So it depends on the method and the applied strain. For the
Variation.
small, it is very isotropic. So it goes back. It's very elastic. So it goes back as you release the strain. That's what experimentally they are found out. So it depends on the method that you apply, or how do you apply. For example,
Well, I'm just wondering, if you look at the stress-strain relations, does it depend upon how you pull relative to the crystalline axes? Right? That's what I mean by isotropic. That's the traditional definition of isotropic elastic response, right?
yeah, this I don't know.
There is a small change, but it's not a big change.
So it's
The
nearly
armchair and the
isotropic.
zigzag have different elastic properties.
Yeah, so for small, which is by definition almost, right, all these ratios, I think it's very close to being isotropic with some angular dependence that is known. So. But for large strain, it becomes very anisotropic, right? But those ratios are defined by definition for small, I guess.
But when you talk about 5% strain,
Yeah.
is that possible? I mean, if you
Yeah.
take an ordinary
So-
material and strain it 5%, it would
Yeah.
completely fall apart.
Yeah. So they have strained in some experimentals I've seen. So this breakdown, the one on the right, the zigzag where effectively a new ground state emerges, actually a gap emerges. That happens, I think, at 25% or something like that. So, and people have pushed it to the limit, and I think they have never seen a gap opening. So experimentally, people have always been below 25%. That's what I know.
From the APS meetings, some of the conversations I had, that much beyond
Yeah.
getting up towards 5, they're starting to have more problems of, they think they could apply more strain, but they're not getting pure enough graphene, that the graphene naturally has defects in it, and it's ripping along those defects before they can strain this large. But I think but talking with them, theory should hold up, that they should be able to get some astronomical strains out of it, in theory.
And there are artificial graphene systems where they are able
Yeah.
to apply even more.
Yeah, so I think we have in mind mostly, I think it's very unrealistic to think that these exact theories will translate to graphene strain.
No, but
because-
there are a lot of systems that people are modeling after graphene, where a lot of these things will hold true, but they're artificial lattice structures and things like that. Yes?
So, if you're looking at bilayer graphene and you're
Yeah.
looking for small strains, have you tried correlating with multi-wall carbon nanotubes, where you have a sheet of graphene that's been bent around to join on itself, and you would specifically deal with few concentric layers?
I see no reason that couldn't work. I've specifically, I've not spent much time thinking about how an experimentalist could do any of this stuff. I've been much more concerned with just what we can do.
Because when you make a nanotube, it is a small strain to your graphene system.
Yeah,
Like you can talk about the strain angle of that.
I suppose. I guess my concern would be, the first concern that comes to mind is if you get any weird periodic things in it, just because.
Well, yeah, the chirality of the nanotube ends up affecting its conductance, so you'd have to choose certain chiralities.
Yeah.
And remember that the armchair and zigzag for graphene is opposite than the armchair and zigzag for nanotubes. because they hate nomenclature in physics, apparently.
Yeah.
Just tossing that out there as something
No,
to look
that's
for
an
correlation.
interesting. Yeah, I could see something like that happen.
More questions? No? Okay, well, we'll continue with the first session. Thank you, everybody. The committee stays here, please.